We're going to ask Stewart to talk to us about the ABC.
Thank you very much, Bob. And start by thanking the organizers and, of course, the man of the hour, Krishna. So very happy to be here on this occasion, honoring Krishna. Okay, so what I'd like to speak about is a very well-known conjecture that has all sorts of implications. To do so, we'll start with a bit of notation. So for any non-zero integer n, let k of n denote the greatest square root factor of n. So it's just the product of primes dividing n. And k of n goes by different names. It's also known as the core, or square root kernel, or the radical of n. And the ABC conjecture, first proposed by Oesterle and Masser, is that for each epsilon bigger than 0, you can find a positive number, a0 of epsilon, which has the property that for any pair of distinct coprime integers a, b, c is less than a0 epsilon k to the 1 plus epsilon, where c is just the sum of a and b, and k is shorthand for the greatest square root factor of the product, a times b times c. Okay, well, this is an absolutely marvelous conjecture. It's extremely profound, and basically the reason it's as powerful as it is that it's capturing in a very succinct way the fact that the additive and the multiplicative structure of the integers, they're independent. So, okay, so one of the areas in which ABC is applied to great effect is the theory of Diophantine equations, but of course there are a host of other applications. Well, I mean, you might ask, for bounds, let's not go for the whole 9 yards, just can you in fact bound C from above as a function of K? And in fact, that does require some work. We did it with Rob Tiedemann back in '86. And then later with Kunri Yu, we were able to at least go some way towards the conjecture. So with the usual assumption, we could show that for all pairs AB, we can bound C from above by exponential of A1 times k to the 1/3 of log k cubed. So basically e to the k to the 1/3, and of course what we would like is essentially k to the 1 plus epsilon. And it may be that this result has been already supplanted by the work of Mochizuki, but that is to be seen, so we'll wait on that. There's a really lovely recent development due to Rem Murty and Hector Paston, using the fact that all elliptic curves over Q are modular. They give another approach to bounding C from above in terms of the greatest square root factor of A times B times C. They're able to prove that you can find an effectively computable positive number A2 such that always we have C less than e to the A2 times k log k. Now, the function is weaker, but nevertheless, the approach is different. It's using the very powerful work that ultimately resolved Fermat's last theorem. And it's fascinating to see that it can be exploited in this way to give a result on the ABC conjecture, or towards the ABC conjecture. Now, in fact, one can actually, in certain instances, do better than the upper bound for C of the form exponential of k to the 1/3, essentially. And let me just explain that. So we'll take this convention. So let P sub A, P sub B, P sub C be the greatest prime factors of A, B, and C respectively. We just take the convention that the greatest prime factor of 1 is 1. And then let P dash be the minimum of those three, PA, PB, and PC. Okay, well, with you, we were able to prove that for each positive number epsilon, we can find some positive number C of epsilon, effectively computable in terms of epsilon, such that with our usual assumptions, C is bounded from above by e to the C epsilon P dash k to the epsilon. So what that's saying is that, now remember before our upper bound was C is less than essentially e of k to the 1/3 times log k cubed, I guess it was. Here we have P dash. So what that's telling us is that if we're in the case when that triple of integers a, b, c has the property that the greatest prime factor of one of them is fairly small, then in fact we can get a substantial improvement on what we have today. In fact, the k to the epsilon term one can make explicit, one can sharpen further. One can replace that with one can replace epsilon essentially by a triple log k over a double log k. And in some sense, that's the natural limit of the method. The presence of that P dash is an unfortunate artifact of the way in which the result is proved. Notice that P dash, remember, was the minimum of PA, PB, and PC. And of course, K is at least as big as the product PA times PB times PC. So P dash would have to be less than K to the 1/3. So we essentially recapture the result we had before. But of course, if P dash is smaller than less than K to the epsilon, then in fact we have a K to the epsilon. Okay. Now, just for notation here, so I don't have to insist that my x's are sufficiently large to make log make sense. So log sub j just is the jth iterate for j bigger than or equal to 2 of the function x goes to the max of 1 on log x. So just think of it as log j times iterated of log of. Well, you get asked for refinements of the ABC conjecture, and many have been put forward. Baker, Van Frankenhuizen, Pomerantz, and others have done so.
Is that Alan Baker?
Alan Baker, yes. The way, in fact, yes, not Roger. Alan Baker's formulation was somewhat different from the standard one, but nevertheless, it's a natural refinement that contains the ABC conjecture. So Van Frankenhuizen proposed that there should exist positive numbers A3 and A4 so that C is bounded from above by, instead of the k to the 1 plus epsilon, now we're asking, well, what is that k to the epsilon term? What should it be like? So the suggestion was that it was bounded from above by k times e to constant times the square root of log k over log k. And in fact, that's really the correct order. That second order term is of that size. So there would be infinitely many pairs AB of coprime positive integers for which C is at least that large, at least as big as k times e to the A4 square root of log k divided by log k. Well, recently, Robert and Tenenbaum have, one's going to make sort of heuristic arguments about the ABC conjecture. The natural function to look at that one needs information on is the function n of xy, which counts the number of positive integers n up to x, whose greatest square-free divisor is at most y. I mean, that's the obvious analog of an incredibly well-studied function, the psi xy function, where instead of greatest square-free divisor is at most y, one just says greatest prime factor is at most y. Well, in an absolutely monumental paper, Robert Tenenbaum gave a very detailed analysis of nxy, and based on this, we formulated with Robert Tenenbaum a refinement of the ABC conjecture. Now, we had various formulations of it, but I will give you one. And it's the following. So this will be a sharpening of the result of the conjecture of Frankenhuizen. So what is it? So the claim is that there exists some real number C1 such that if A and B are coprime positive integers, C and K as before, C is bounded from above by K, well, that's the standard thing. And then we have this function here, e to the 4 times the square root of 3 log k over log k. That's sort of the principal part. And then we have two further terms here. Three further terms. 1. So plus, and the next two terms we believe are triple log of k divided by twice double log of k, and then this C1 divided by log k. And in fact, if one's going to go to that level of precision, one better expect that in fact the assertion here holds. In other words, we believe that there's a real number C2 and infinitely many pairs of coprime positive integers for which the opposite holds, for which this holds, but now with another C2 instead of C1. Okay, so that's the conjecture. And what's it based on? It's really based on one fundamental heuristic assumption, and then the work of Robert and Tenenbaum. So the heuristic assumption is that whenever A and B are coprime positive integers, that the greatest square free factor of A plus B is statistically independent of the greatest square free factor of A and the greatest square free factor of B. So this is the basic assumption, and then the rest is, follows. Well, okay, before one goes to refined conjectures, maybe one should do some computation. And there has been a lot of computation done to test the plausibility of the ABC conjecture. And the most extensive project in this regard is one based at the University of Leiden called Reckon Mean ABC. It's a distributed computer program. So basically what they do is they farm out sections of the triples to test. And so people with spare cycles that want to take part in this enterprise do so. And then Bart de Smet, who's running it, makes sure that everything is collated properly. Well, you know, there's a massive amount of data there. And what you'd really like to know is, okay, well, you know, most triples aren't very interesting. You'd like to focus on the ones that are exceptional. And there are two quantities that have been introduced to measure whether a triple is exceptional or not. One of them is the quality, which is just log C over log K. And that's sort of measuring whether the first term, the power of K, is correct. And the other is the merit, which is Q minus 1 squared log K over log K. And that's looking into whether that second order term, the 4 root 3, well, actually it's the square of that, so it's 48. It is the correct term. So as I said, Bartlett Smith is looking after the website to keep track of these exceptional triples that come in. And the largest known quality of a triple, so that's the question of whether the power, the first power is the correct power on K. That's roughly 1.63. And essentially, no triples, in fact, there are 5 triples known with quality larger than 1.55. And for each of those triples, C isn't that big. It's at most 10 to the 16th. So things are trending towards 1, but at a slow rate. Okay, well, how about the other one, the merit there? So if conjecture A is true, so our conjecture with Robert and Tenenbaum, then the lim sup, as we range over all these pairs A, B of distinct coprime integers, is 48. Well, what's the data tell us? So far, 19 triples have been found with merit larger than 30, and each of those has C at least 10 to the 20. So they're all much bigger. 83 with merit larger than 25, and the triple with largest known merit at the moment was found by Ralph Baltz, and it's this enormous guy, which has merit roughly 48, 38, so 38.67. Okay, so something different is happening here. If the conjecture is true, then in fact the good examples are approached way farther out. Well, what can one prove here? We can actually prove, this is something I did with Rob Tiedemann a long time ago. One can show that, well, there has to, you can't get by with just K times the power of log. In fact, there are infinitely many pairs of coprime positive integers for which C exceeds K times that function, e to the essentially 4 times the square root of log K over log K. Okay, now the issue here is that term log K isn't under the square root sign. So that's the deficiency in this result. And then in 2000, Van Frankenhuizen was able to replace the 4 minus epsilon by 6.068. And he did so by replacing essentially a pigeonhole principle with a geometry of numbers argument, which was more efficient and involved sphere factor densities. Okay, so conjecture A, remember, is established under this heuristic assumption that whenever A and B are coprime integers, the kernel is distributed as if A plus B was a typical integer of that size. So just a first remark before I just give an indication of how this would go. If A and B are coprime and A plus B is equal to C, then the nice thing is that the greatest square free factor of the product, A times B times C, is just the product of the greatest square free factors. Okay, so just to fix ideas, let's think about the upper bound in that conjecture. And let's look at the quantity P of xz. So that's the sum over the pairs AB, where A is between x and 2x, B is less than A and B are coprime, and the greatest square free factor of A times B times A plus B is at most Z. So we're going to estimate that. This is our sort of statistical assumption here. We'd like to bound that from above by the sum, where what are we looking at? We're looking at 1 over x times this n of xy function which we introduced, the number of integers up to 4x whose greatest square free factor is at most z divided by ka times kb, minus the same function but now at x and z over ka kb. Okay, so this is we'd like to control this, and what we need to do is we need to go to the results of Robert and Tenenbaum on the nxy function. So to get our upper bound, it suffices to show that for some z depending on x, so we'll think of this as x over gx, we're going to have the sum r bigger than or equal to 1 of this probability between 2 to the r and this z of 2 to the r be less than infinity. Well, what that would tell us is that this KABC less than or equal to z for some pair in the interval x, in these dyadic intervals, would be realized only for a bounded number of integers x. And that's similar in spirit to the Borel-Cantelli diagram. Okay, so a little bit about nxy. So this is just this. Once again, it's the counting function for the number of positive integers up to x whose greatest square free factor is at most y. Well, to understand it, one can, we introduce this psi function, which is the product p divides m of p plus 1. And the key function is the function f of t, which is 6 over pi squared times that sum m bigger than or equal to 1 of the min of 1 and e to the t over m divided by psi m. It turns out that nxy is very well approximated by y times f of v, where v is log of x over y. So for a wide range of pairs, xy. And this is something that already was in one of Tenenbaum's students, Squali's dissertation thesis from '85, but was formally proved by Robert and Tenenbaum in this very large paper, which was published in 2013. So f of t is the function that's controlling the behavior of this nxy, and it has this nice, fairly nice expression. It's essentially e to the square root of 8t over log t, but one can be much more precise. Then there's an expansion involving these polynomials qj, and the first couple of them are written on the screen there. Well, more precisely, if yx is this function e to the 1/4 square root of 2 log x, log x to the 3/2, then what Robert and Tenenbaum showed is that nxy is actually asymptotic to yfv in this range for y bigger than that.
What is v?
V is log x over y. And so, and also the upper bound there is universally applicable. Okay, and these are sort of the ingredients that go into establishing the upper bound of the conjecture. Well, okay, I'd like to switch focus a bit now and talk about the ABC conjecture in number fields. So many proposed generalizations to algebraic number fields have been given. Goethe, Elkies, Broberg, Granville, Stark, Brovkin, Nasser, and others. Okay, so let me introduce a bit of notation here. So let K be an extension of Q of degree D. Let theta K be the the ring of integers of k, r the rank of the unit group, delta k the absolute value of the discriminant. Here, this is pretty standard. Mk the set of places. So for each place, we choose a valuation. This is just normalizing the valuations in the standard way. For finite places, again, the standard normalization in terms of the norm of p to the power minus the order of p for any alpha k, non-zero. Okay, we're going to be in a position now to introduce the height of a triple ABC. It's just the product over these valuations of the max of the three quantities A, B, and C. That's the height of the triple. The radical corresponding to the greatest square free factor of ABC, that's just the product over the norm P or PP, where the star indicates the product is taken over those finite V's, valuations, for which all three of them aren't the same. So this corresponds basically to the radical we had before, the greatest square root factor of ABC. And so if k is of degree d over q, then the conjecture is that for each epsilon bigger than 0, there exists a positive number c which depends on epsilon of d, such that if a, b, c are in non-zero integers in k, non-zero elements of k, for which a plus b is equal to c, then the height of k is bounded from above in terms of, now we have a discriminant in there, delta k, the radical raised to the power 1 plus epsilon. So that's the number field analog. Let S be a finite subset of Mk which contains all the infinite places. Theta S star, the group of S units of K. The equation alpha x plus beta y equals 1 in x and y in theta star S is an S unit equation. Many Diophantine equations can be reduced to things of this form. So Jury was able to give an upper bound, explicit upper bound for the heights of solutions of these. Then I list some of the people who worked on improving bounds subsequently. Now we get back to ABC. Soroka was able to give an upper bound for the height in terms of the quantities we've introduced here. It's exponential again, and essentially it's the discriminant times the radical to the power constant times d, whenever we have an ABC triple. She used estimates of Bugeaud and Jury. Jury, a year later, was able to sharpen it, and notice the difference here. This is height of k at most, some constant C3, so let's suppress the dependence on delta k, times the radical to the 1 plus epsilon. So e to the radical to the 1 plus epsilon. So in the case of k equals q, we don't recapture the result we had with Kunri U because it's not k to the 1/3, but nevertheless it's of the same shape. He also showed that if we could take nk large enough, then in fact we could have a result where it was of the form the height was at most the exponential. Now we have the discriminant inside that power 1 plus epsilon. So it's made explicit. But again, the radical. These results rely on estimates of Jury and Yu on S-unit equations, and ultimately they depend on estimates of Matveyev and Yu. Matveyev for complex linear forms and logarithms, and Yu for chaotic versions of them. And this is basically the approaches, the method of proof is similar to the proof that applies in the radicals. Okay, I'll stop there.
Your formulation for the algebraic number field case depends on the field, is that right? You're not using the absolute formula.
Not the absolute formulation. There is, no.
And indeed, Machitsuki is not only claiming ABC, but for all number fields as well.
Wow.
I believe the proof requires that.
Further questions? Well, thank you very much, Karen.
My point is, he's going to require to use absolute normalization for the height.
Well, I mean, it would be spectacular, as everybody knows.
So what about, I mean, in some sense, ABC is careful, right? I think ABC is random. It's true.
Absolutely, yeah.